Hello. In this video, we're going to explore potential energy functions. These are required if we're going to be able to evaluate BT um, and therefore be able to get an equation of state for the dense gas case. Um, so we'll look at some simple algebraic forms here, along with a more realistic form called the Lennard-Jones potential. So here are plots of three very simple potentials and Lennard-Jones. The first is rigid sphere. You might think of this as the billiard ball approximation. There's no force between particles until they actually hit each other, and they can't penetrate. So the potential energy just looks like a delta function at the distance between when the two balls touch. The square well has an attractive portion and a repulsive portion. The attractive portion is just represented as a square well, hence the name square well. So algebraically, it's extremely simple. Weakly attracting potential has some kind of curved section of attraction here, and typically it's represented as some kind of exponential. And then the more realistic potential is the so-called Lennard-Jones potential. We'll see what it looks like in a bit, or see what the function is that is called the Lennard-Jones potential. But it looks like what we know the real potentials to look like, more or less. Okay, so recall that b of t is equal to minus 2 pi the integral from 0 to infinity of f of r dr. So we can just go ahead and plug in the potential into f of r. And for rigid sphere, this is the expression we get. We can divide it into two parts, the repulsive part and the attractive part. And if you just run the integrals out, you get the bt is 2 pi sigma squared, or sigma cubed, sigma cubed over 3, where sigma is the collision distance. It's the distance between the centers when the two particles are touching each other. So note that the volume occupied by a spherical molecule is 4/3 pi r cubed, which can be written as 4 pi or 4/3 pi sigma over 2 cubed, because sigma corresponds really to a diameter. If you have two equal sized particles, sigma is the diameter of one of the particles. And this is called the covolume. So it's the volume excluded to other molecules. Think about a bunch of pool balls or billiard balls on a table. Once they're touching, you can't get them any close together. It's just because they can't fit inside of each other. So B of t is 4 times, B of t in the hard sphere approximation turns out to be 4 times the volume of a spherical molecule. Now we can write P is equal to RT over V plus RTB over V squared plus higher order terms if we so desire. If B is much less than V, and if we substitute the lowercase b for capital B, and I'll explain why in a moment, then we can write P is equal to RT over V minus B. And we use lowercase b just because it's conventional. If you look up van der Waals equation, you're going to see lowercase b there. So this is the first term in van der Waals equation, and it represents the addition of a repulsive term to the ideal gas relationship. Now, if we go to weakly attracting spheres, and you can see the function, the attractive portion of the function in this integral, and evaluate b of t, then it turns out that b of t can be written as lowercase b, the previous lowercase b, minus a over rt. And the a over rt represents the contribution to the attractive term that comes from adding that to the weakly attracting sphere model. So if b is much less than a over rt, then you get van der Waals equation, P equals RT over V minus B minus A over V squared. So the first term, adding B, essentially adds in the repulsive portion of the of the potential energy function, and the second term minus A over V squared adds in the attractive portion. So I just have to say, I love van der Waals equation because it really very simply illustrates the physics of PVT relationship. As you try to increase the density of the gas from the ideal gas limit, at first it actually becomes easier. You need less of a pressure increase to accomplish a certain increase in density because of the attractive forces. But if the particles get too close to each other, then the repulsive force dominates and a much greater increase in pressure is needed. So that's it for this video. Thanks for listening and have a great day.